Now, waves also have some properties that are intriguing that when they hit a boundary, and that might just be, it may not seem like a big boundary, but something that's more dense than what it was traveling in, it's going to change the speed. And the density between those two media that it's traveling in is big. The bigger it is, the more likely all of the energy is going to just bounce off. We saw that in momentum, a small thing hitting a big thing. If you've ever watched those fails on exercise balls, the small person running into a big person totally gets knocked off their feet. Well, a wave is a small thing. If it hits something that's not moving, most of the energy will just return back. But it depends on how the end is, if it's open or if it's closed. Now, a string, like the slinky we had, may be attached, and you'll see that the reflection comes back when it's attached, but it'll come back inverted. So as it goes in this way, it's going to hit this end. It's going to stay still, but then it's going to come back on the opposite side. So I've got a slinky here, which we'll turn just real quickly. We'll take a look just at one wave return. And if you can see it, maybe, I'm not sure if you can well, but I'm going to pull it towards me this way. You can see that it flips sides on those. What does end up being an interesting case is that the worst place, let's say as a surfer, if you get in close to shore, or if you have an accident and you've hit next to a cliff, that those waves coming in actually will hit those, and because that's an open end, actually the waves are the very tallest there because you're meeting both the incoming and the outgoing wave together, and they end up being quite large. If you're on top of that wave and then it comes back down, it's going to also be quite low on the other side, is that you have this chance to be smashed into the rocks. And so that is a most dangerous place in terms of being involved with waves, because the wave action is actually being constructively added up. Now, if an end is open like this, now where would a reflection like that actually happen? Well, the end of a tube that was producing sound, like at a flute, the end would hit that, and it's open, and that would allow the wave to come back, but it wouldn't change shape. And that does change the frequency of which something might resonate. We'll talk about those in instruments here in a little bit. These two kinds of tubes, one, if you're like blowing on a Coke bottle, that's a closed end reflection. But if you're blowing on like a flute or a penny whistle, those are open. They'll change where you have to cut the holes in the top to get the resonance to be of certain notes. I've left a little YouTube here for you to see examples of what we're talking about in that case. Another phenomenon that is typical for light. Light is going to slow down as it gets closer, or shallower waves that are on, for instance, the water, or if light goes into something that slows it down. Light travels the fastest in space, but as soon as it goes to other media, it's going to slow down a little bit and transfer slower, and travel slower. But if you look out into this, in the example of your notes, you can see the waves in the middle of this area. That's a lake, a little finger of a lake that's coming in. You can see the waves are moving just parallel to the shore. As you get closer, though, those waves are getting a little bit of friction, and they're coming in a different direction. And as you get real close to the shore, you see that those different directions are in here. So that the direction of the wave travel is this way, whereas it gets close to shore, or as it gets really close. Another way to think of this is a group of soldiers marching, or people in a band that are marching, and as soon as they get into something like a march or something that's slower, this end starts slowing down, and it ends up turning those marching lines. You can see the direction that this column marching people are going is this way, or that once they get into something slower and deeper, that'll cause them to turn. It happens with a car too. If you're driving in like a little toy and it hits something like grass, it'll turn and go into there. Those are different. Refraction is bending of light when it changes the medium it's in, that it travels slower or faster. Now, that rate of how fast a wave can travel in one kind of media to the other is called a refractive index, and I'll get into that. We have it as a formula when we do problems. Okay. Diffraction is a little different. Refraction is light slowing down and changing directions because of the media is changing. It can only travel slower. Well, diffraction is when waves spread out when they hit a corner. Now, thankfully for us, sound is a good example. Sound is a slower wave, and so compared to light, it'll go out the door and it'll spread around. So if you need help, you're like, hey, come back in the room, that you'll hear that outside in the hallway because the wave spreads out. Here's a good example of waves crashing in this direction. And as they come around, they'll actually turn around. So the waves are coming towards us here. And then what's happening is the waves, as they come around this corner, are going to go from here. And they're going to start to change directions. And they'll crash all around a point. That's actually what causes that erosion, is that, as it cuts around like this, it cuts more away on this other side. And that becomes a headland. Here's an example of waves coming through two islands. As they do, what ends up happening is these spread out this way, okay, and these waves spread out that way, so they'll create these sort of semicircle of waves because they're bending as they go through a cut. And as a matter of fact, we usually use that advantage by cutting something in a material like plastic. We'll make little cuts, or we'll even stretch molecules so that they end up becoming a grating. That grating is called a diffraction grating, and if you've maybe heard of the word CDs, CDs are such that they cut grooves into plastic material, and that is encoding messages on there. So the way that these light bend as they come off is what makes the media from which we create CDs to listen to movies or store, information in computers. So slower waves are going to diffract a little bit more depending on how fast they go. So that's what I was talking about. Light doesn't diffract much when it comes through a window. It doesn't spread out much. You don't see a lot of diffraction. But if you make those cuts small enough, the smaller the size of opening is also going to increase how much the spreading happens. So we'll see when we cut some things that are small that we can put in small enough slices in there, you'll really get a diffraction that will cause light to spread out. Okay, resonance. Resonance is interesting. Resonance is when a wave is passing through something and it's the natural vibration of that object or that media. For instance, I'll just take this slinky, and if I get this to vibrate carefully, if I start to add these, it'll get to a place where one frequency sort of naturally vibrates in here and it builds up. As I just give a little bit of push, this keeps this shape going. If it isn't that natural frequency, it'll just pass right through. So what are some examples of those? And I've included a couple of the YouTubes. Is that the wind was blowing one in the late 40s, I think this was 1948, by a brand new bridge that had finished, but the wind was just such that it would cause a little bit of vibration in the way the bridge stood. And then as the wind blew, it actually would keep pushing it, just like you're pushing a swing, and every time you pushed it, it got bigger and bigger. Finally, this had tore apart, and that's the Tacoma Narrows Bridge that you can find online examples because they filmed it. The news crew came out and got film on it in the late 40s. You can also see that was part of the problem in Mexico, is that certain size buildings resonated by vibrating back and forth at about the same rate that earthquake that came through. Not every building fell, and it's the same probably in this one, although I haven't seen an analysis. Obviously, it's only been a month since that earthquake came through. But which buildings fell were the ones that resonated with the passing of that earthquake. The last phenomena that we'll talk about before we get into sound is what's called the Doppler effect. Now, if you take a look at the Doppler effect, just means that your source of your sound is moving as well, and if it moves, even at a quarter of the speed that sound does, 340 meters per second, I mean, even if it's a tenth of that, it's going to make this sound that's coming from it because it's pushing a wave, and then it'll move forward and push the next wave. Now that distance between troughs, in terms of noise, is closer, and so to your ear who's standing there, you hear the waves crashing into your eardrum even faster. That speed will then cause that pitch. What we're going to learn is, when we're talking about sound, is pitch goes up when the waves are coming in faster. Pitches like A versus B versus C, those are higher pitches on the piano. Now, you see this all the time if you're a fan of racing. As the cars come by, they'll go because the sound of their engine is high. As it's coming towards you, it has a higher sound to it because the vibrating engine's making it sound like a higher pitch. And as it passes you now, between every wave, it's actually driven further, and so it makes the waves farther apart and makes it a lower pitch as it passes. Or an ambulance that passes. So those are examples of the Doppler effect. When we get into sound here in a bit, we'll explore those by formula. There's a couple of examples of problems. I just want you to differentiate between these kinds of phenomena, whether light is bent because it goes around a corner or if it's going to slower media, just so you get the hang of that vocabulary. The next several questions on the sheet for today is to differentiate these types of phenomena.